The Doppler effect describes the perceived changes in sound or occasionally light when two sources are either moving toward or away from each other. And the most traditional way of teaching the Doppler equation is this down here, which involves a plus and a minus of the object and the source. And you have to remember what is a positive and what is a negative if they're moving toward each other or away from each other. And while this can definitely work well for you, I think it's a lot easier if you simply understand why the Doppler effect occurs and what it is measuring. So the first thing to realize is that our ears aren't things that intake sound waves and capture them and measure the exact wavelength and frequency, but instead it's kind of a shortcut. We're accustomed to sound waves in air that travel at 343 meters per second. But what our ears measure is the number of vibrations that happen every second. So they use the number of vibrations as kind of a stand-in for the frequency and the wavelength. And the frequency tells us about pitch. And then we just kind of base all of this on the assumption that the sound wave is traveling 343 meters per second. However, when there's a moving source, that might not be the case for that sound wave. So in this example here, what's happening is that the sound wave, which is still a 343 meter per second sound wave, is getting 30 meters per second added to it because it's being released from a moving vehicle. And the moving vehicle adds that 30 to the 343. And what that does is that increases the speed of the sound wave by 10%. It was once a 340 meter per second wave, and now it's 370. But what our ears encounter is that it seems like more wavelengths are hitting us, and so it seems like a much higher frequency one because it oscillates more every second. And so that underscores something, that if you have about a 10% change in the speed of the sound wave because of this vehicle, it's going to have about a 10% change in the observed or perceived pitch, which is a part of frequency, and also the perceived wavelength. And so it is perceived differently due to the fact that the wave is traveling at a different speed. And so a much better way to think about the Doppler effect is looking at the relative velocity between these two objects compared to the speed of the actual wave. So in this case, the relative velocity is going to be 30 meters per second toward each other. And when you look at 30 over the speed of sound, which is around 340, you're looking at about a 10%, bit less than 10% change. And that means that it will seem about 10% different than its actual frequency, and it will seem about 10% different from its actual wavelength. And so the observed or perceived wavelength is going to be different. So the next question you have to ask is whether the wavelength seems smaller or whether it seems larger, and same with the frequency. And the way to approach that is just to realize that if the objects are approaching each other, then the wave is perceived as being a tighter wave, which means a higher frequency but smaller wavelength. And so because these are moving toward each other, it's going to seem like a wave with a far greater frequency, about 10% greater frequency, and a lower wavelength, about 10% lower wavelength. And so you can plug in those numbers, 30 over 343. And if we knew the actual frequency, then we could just figure out what this observed change was, and we would know whether we're supposed to add that to the perceived frequency or whether we're supposed to subtract that from the perceived frequency. And that's how the Doppler effect works. It's basically because we are so accustomed to sound waves being at 343 meters per second, if you speed up the sound wave or make it something that is not a normal sound wave, then we're going to perceive it in a different way, as though it were a normal sound wave, but with different qualities. The things to recognize are that the relative velocity cares about the speed of both components. So if the ambulance was moving 30 meters per second this way, but the person was moving, let's say, 5 meters per second toward the ambulance, then what it would be is a 35 meter per second relative velocity. They'd be getting closer at 35 meters per second. If he was running 5 meters per second in the opposite direction, it would be approaching at 30, but they would be getting further apart at 5 meters per second. So your relative velocity here would be 25. Note that the sound wave would still be traveling at 343. But if you change the numerator here, then that will change the amount of difference that is perceived by the observer, because it is a smaller fraction compared to that if their relative velocity isn't as great. Now, you often see the Doppler effect with sound a lot more frequently than you see it with light, and there's a reason for that. It's hard for any sort of man-made vehicle to travel at something that is even close to 10% of the speed of light. And so oftentimes vehicles or jets or moving objects can make a meaningful difference in how fast a sound wave travels. It might increase it or decrease it by 10%, and that will have a noticeable difference in how it's perceived. For light differences, you're looking at something that's 3 times 10 to the 7 meters per second. That's very, very fast just to see a 10% change in the observed light. The only time you'll probably see that is if you have objects in space that are moving toward or away from each other at astronomically high speeds. But the bottom line is, with the Doppler effect, if you just remember this, remember that the relative velocity of the two objects, and that is either moving together or away from each other, if you divide that by the speed that the wave naturally travels, like 343, then that will give you the ratio of what percent or what proportion of change you observe in the frequency and in the wavelength. And then as long as you remember that if the sources are approaching each other, the frequency seems greater and the wavelength seems smaller, then you'll be good to go with any Doppler equation that you'll encounter on the MCAT. Even if it doesn't cover as many examples as this, it will cover anything MCAT relevant if you just understand it this way, as the objects adding to the speed of the wave.